we're just going to go over this. And again, I made this yesterday, so make sure that you guys are like, one, look over it before the exam. Two, make sure that you guys are going to use it for the exam. If you guys can't read anything, just like zoom in, zoom out. This was made on a pretty small tablet. Okay, so again, let's go over kinematics. Kinematics, again, this is super duper important, right? Like, there are equations for kinematics. You don't need to memorize them. They're here, right? They're on a formula sheet. Make sure that you guys just like know when to use them. So the first equation, the v is equal to dt, is when acceleration is 0, right? When there is no acceleration, when there is no change in velocity, use this equation. Okay, super important. When the acceleration is not at 0, right? When there is a change in velocity, you use this, right? Pretty simple stuff. Again, as long as you know 3 things, you know everything in kinematics. Also super important is to understand like how vectors work, right? So if you're going to break something up, this is the sine component, this is the cosine component. Make sure you guys know that to be able to do these problems. Okay. So now let's look at graphs. Okay, graphs are going to be are pretty important. They're probably going to be on the test. So these are the graphs that you might see in kinematics problems. So we're going to go over them, right? So the first graph I have here, right, the graph on the top right corner, is a position versus time graph. Okay, so the y-axis tells me the position of the object, right? Where is the object in relation to 0 or relation to where it started with, right? So the x stands for the position, and obviously like the x-axis stands for the time, right? So this is a position versus time graph. So again, the position versus time graph tells us a lot of things, right? So the first one is the slope, or actually the only thing is the slope. The slope of the graph tells us the velocity. Repeat, the slope of a position versus time graph tells us the velocity, right, of the object. It's how fast it's going. So if the line is a straight line, right, if it's a linear line, we know that the velocity is constant, right? So if the slope tells me velocity, if we have a constant slope, right, if it's going to be a straight line, that means the velocity is also constant, meaning there is no acceleration. But if like the graph is curved, right, if the graph is curved like this or like this, right, then there must be an acceleration, right? There must be change in velocity because the slope is changing, right, in these kinds of graphs. Okay, so again, the slope tells us velocity. If the slope is the same throughout, if it's a linear line, that means there's no acceleration. But if the slope is not constant, if the slope is getting steeper and steeper, or less steep and less steep, or flatter and flatter, right, then we know that there is an acceleration, whether it be a positive acceleration or a deceleration. Okay. Next one is a velocity versus time graph, right? So a velocity versus time graph is the y-axis tells us how fast it's going at a certain point, right? So if this is 2 seconds, right, and let's say this is 5 meters per second, then we know that this object at 2 seconds is traveling at 5 meters per second. Okay, so that's super important. So a velocity versus time graph, 2 important things there is the slope and the area. Okay, the slope and the velocity versus time graph tells us the acceleration. So the slope of this line, right, the slope of this line is the acceleration of the object, right? It's the how fast or how slow the object is at accelerating. Okay, so again, if the line is a straight line, right, or a linear line, then that means that the acceleration is constant. If it's not a linear line, then that means acceleration is not constant, right? You might also see something like this, right, in the velocity versus time graph. So if you notice here, like the velocity is not changing, right? If this is 5, then the velocity is 5 this whole time, right? So that means there is no acceleration when the line is horizontal. Okay, the other important thing is the area. The area in the velocity versus time graph tells me displacement, right? So if I wanted to find the time, like let's say at 2 seconds, and like let's say this is 4, right? I would have to find the displacement. I would have to find the area under the curve, okay, which is just 2 times 4 divided by 2 because the area of the triangle, right? You can also have done this problem using kinematics equations, right? You can, if this is like 4, right, and this is 0, and this is time like 2 seconds, okay, you have your final velocity, you have your initial velocity, and you have your time. So you can use one of the kinematics equation to solve for change of x. Okay, so you can do that too. So if you're not comfortable with just like trying to look at the map or look at the graph and know what to do, you can also apply your kinematics equations to it. The final thing is acceleration, right? So this is the acceleration versus time graph. Important thing, in acceleration versus time graph is the area. The area in acceleration versus time graph tells me velocity. Okay, so all of those things are important, and again, you can use this for the exam. So if you forget, if you're unsure, just look over this for the exam, right? So again, it would be really helpful if you guys can print this out, especially since like I made it all black, right? Is to have a separate sheet of paper to work on it, or a separate like device to work on it. Okay, whether it be like a phone or another computer screen or a tablet. Okay, so that's pretty much it for kinematics. So let's move on to forces. So I wrote a lot of things about forces. So again, like it really help if you guys like look over this beforehand. So like let's say you're taking the exam and you're like, oh, I remember this will be in our notes, so you don't have to look at like the entirety of the notes, right? You know more or less where it'll be. So it would really help if you read this or if you look at this beforehand. Okay, so forces or dynamics centers around Newton's laws of motion, right? His first law of motion, where it says an object at rest will stay at rest, or an object in motion will stay in motion with that same velocity in that same direction unless acted upon by an unbalanced force. So that means, right, if there is no if there is no net force, right, if one side is not winning out, then that means there's no acceleration, right? Meaning either the object is going to stay at rest, or the object will keep on moving in that same direction forever, right? So in space, if I throw something with an initial velocity of like 5 meters per second, let's say, right? If I throw something with a velocity of 5 meters per second, since in space there's no air resistance, there is no gravity, right? There's nothing affecting that object. It will keep on going at 5 meters per second forever until an unbalanced force acts on it, whether it hits something, right? Yeah, so again, right, this is super important. Unless there is an unbalanced force, right, meaning like one side is winning out, then there will be acceleration, right? If there is no unbalanced force, if the net force is 0, there is no acceleration. That's where this comes from. Like some of the forces is equal to ma, and some of the forces is equal to 0. We use some of the forces is equal to ma when acceleration is not 0, and we use some of the forces is equal to 0 when acceleration is 0. Okay, so important, like the different types of forces that we'll see friction, tension, normal force, air resistance, applied force, and spring force, right? When we're talking about contact forces. Again, we talked about this last time. Contact forces is when you're actively like touching something, right? When there's a touching that happens, there's a contact that happens to apply that force. Field forces, or non-contact forces, is like gravity, electrostatics, and magnetic forces. So let's go over like the different kinds of forces. The applied force is, we'll see it as like the pulling of something or the pushing of something, right? So like when you're pulling a box or you're pushing a box, those are applied forces. It will be, you can denote it many different ways. I like to denote it as F subscript APP or F subscript A. Okay, doesn't really matter. Normal force is the force that is applied to an object when it's resting on a surface, right? So right now, your chair that you're sitting on is applying a force on you in an upwards position, right? So again, according to Newton's first law of motion, an object at rest will stay at rest unless acted upon by an unbalanced force. Right now, you're at rest. You know that like gravity is pushing you down, right? So that means gravity is pushing you down and you're not moving, right? It's not like you're sinking downwards. That means there must be a force balancing out gravity, and that force will be the normal force coming from your chair. Okay, and it always will be perpendicular to the surface. Okay, so if your surface is right here, right, your normal force will be in this direction. It will be perpendicular, meaning 90-degree angle with the surface. Okay, and it's denoted by the letters Fn, right, or N. Doesn't really matter. Frictional force is the force that resists the motion, okay? It's always going to be in the opposite direction of the motion. So if you're, like, let's say you're driving a car, right? The force of friction will be in the other direction. That's why when you're driving a car and you stop pressing on the gas pedal, right? There's a reason why you slow down. The reason why you slow down is because there's an unbalanced force affecting you, right? Because again, according to Newton's first law, right, once, like, let's say there's no friction, right? Let's say there's nothing affecting you. Once you let go of the gas pedal, let's say you're going at like 60 miles per hour, you're going to keep going for 60 miles per hour forever and ever and ever. But because you don't, right, there must be an unbalanced force that is affecting your car. And in that case, it would be friction. Okay? So friction is this unbalanced, is this force that is affecting the motion of your car, right, in the opposite direction. So if your car is moving, let's say west, force of friction will be moving in the opposite direction. Okay, so again, super important. It always resists the object's motion. It's always applied opposite of the direction of motion. We're gonna have two kinds of frictional force. We have static friction and kinetic friction. Static friction is the friction of an object at rest, and kinetic friction is the friction of the object in motion. It's also super important to understand, and included a graph here, like the force of friction is stronger with static friction. Okay, so like and again, like you probably noticed before, when you're pushing something very, very heavy, right? It's really hard to get to move. But once you move it, it becomes a lot easier, right? You don't have to push as much. But that's because of the difference between static and kinetic friction. Static friction, you will have to overcome that force. That's why there's this graph here, right? The force that you would need to overcome, static friction is all the way, is all the way up here. But once you overcome that force, right, it becomes a lot less with kinetic friction. So when you guys are seeing like the coefficient of static friction or the coefficient of kinetic friction, the coefficient of static friction will be greater than the coefficient of kinetic friction. Important thing about like friction forces is this equation, the fun equation. The force of friction is equal to mu times n. Okay, so that's mu is the coefficient of friction, and n is the normal force applied. Next is the tension force, is the force along a rope or a string. Okay, so if something is held up by a rope, there's going to be tension. Pretty simple. Okay. Next is spring forces. Spring forces is the force applied by a compressed spring. Right, so we talked about the force applied by a compressed spring. So it's dictated on two things. It's dictated on the spring constant, right? So again, there are some springs that are harder to pull, right, than other strings, right? Some strings are like super easy to play with, right? But some are like pretty stiff, because the ones that are stiff have a higher spring constant. So with frictional force or with spring forces, we go by this equation. F is equal to kx, right? So the force of a spring is dictated on the spring's constant and the displacement, right? How much are you stretching it by, right? How many meters are you stretching it by? How many meters are you compressing it by is what x stands for. So the force of the spring, and again, that should make sense, right? When you're stretching and stretching a spring, it gets harder and harder to stretch because the spring is putting in more and more of a force as the further the x, right? The further you're stretching it. Same thing when you're compressing it. It's really hard to compress and keep compressing a spring, right? The further you go, the more force that the spring applies on you. Next is gravitational force, right? Or weight. It's the it's the force applied by gravity, right? It's dictated on the mass, right? The object's mass, and gravity, right? So the gravity is 9.8 or 10, right? Make sure that you know that we can use 10, especially since, so we can use 10. So just know that like the gravitational force, is dictated by the mass of the object. So we do mass times acceleration due to gravity to find the weight or the force of gravity that's acted on the object. Very important, it's always pointed downwards, right? So like we had questions like this in the beginning of the year. So like let's say an object is flying, right? An object is thrown or kicked, and let's say it's over here, right? So let's say the ball is over here in this position, and it's going to have this path, right? So you're gonna say like, hey, what are the forces applied to this object? Well, the only force that's applied to this object, assuming that air resistance doesn't exist, is gravity, right? And gravity is always pointed down. I repeat, gravity is always pointed down. Next is the free body diagram. So the free body diagram is a diagram that shows all of the forces that is acting on the object. So when they tell you to draw a free body diagram, let's say they're asking you to draw the free body diagram of an object at a ramp, well, you're gonna write down all of the forces applied to it. You're gonna write down gravity because it's always pointed down. You're gonna apply normal force because it's perpendicular to the surface. Let's say it's being being slid down, so you know there's going to be a force of friction. And this is the free body diagram, right? This is the actual free body diagram of the object, but sometimes they might ask you to split up forces, and then you would have to split up mg. And that's like, remember, sign goes with slide. Super important. Make sure that you guys remember that. Sign goes with slide. So, also, super important, each force is represented by an arrow, and the larger the arrow, the bigger the force, right? You're showing a bigger magnitude if you're showing a bigger arrow. Pretty simple stuff. Next is Newton's first law of motion. We talked about this already. So let's go to Newton's second law of motion. So Newton's second law of motion just talks about this equation. Sum of the forces is equal to ma. It just like explains what this equation means. So this equation, all it shows, remember what I told you guys in the year, algebra is all about the relationships between the variables. So the second law of motion talks about the relationship between the sum of the forces, the net force, mass, and the acceleration. And Newton's second law of motion says acceleration and mass are inversely proportional. Meaning, if this stays the same, right, and let's say acceleration goes, let's say like the amount of force is staying the same, and let's say mass goes up, then that means acceleration goes down. Pretty simple stuff. Okay, it just shows the inverse proportionality between mass and acceleration. Newton's second law of motion is pretty much the equation F is equal to ma. Okay. Next is Newton's third law of motion. For every force, there's an equal and opposite reaction, right? If you apply a force into something, it applies that same force, right, in the opposite direction. Again, if you punch someone's face, their face will punch your hand right back with an equal and opposite reaction. Okay. So, for example, let's think about this. So, for example, the reason why you can walk, right? The reason why you walk is because when you're walking, you're applying a force, right, in one direction, and the force of friction is applying a force in the other direction, which is the reason why you're being propelled forward. Same reason with like when you're swimming. When you're swimming, you're applying a force, and then the force, water propels you forward because it's applying an equal and opposite force, or an equal and opposite reaction. Okay, so that's the idea of the Newton's third law of motion. For every force, there is an equal and opposite reaction. Next is inclined planes. We talked about this just like a few seconds ago. Remember, like this is typically going to be right here. It's typically going to be the free body diagram for it. But again, sometimes they're going to tell you to like split it up. And again, gravity is split up by its sine and cosine component, right? So you're going to see here is like the sine component is the one that's going with the slide, and the cosine component is the one opposite of the normal force. And then what you're going to realize here, or like, wait, it's not moving up in the normal force direction or down in the mg cosine theta direction. So you know that like there is no acceleration happening in this axis. So what you realize is like the normal force and the mg cosine theta are equal. Okay, so if you know mg and you know the angle, right, or this angle right here, then you know like what the normal force is, and then you can find out the force of friction, and then be able to solve the problem that way. So next is energy. It's the ability to do work. Okay, so that's what energy stands for. It's an object's ability to do work. Okay, so the unit will be in joules, right? The unit will be in joules, and there are a few equations that we need to know, but let's go over like the different types of energy that we're going to see. Okay, so the first thing is kinetic energy, right? So the kinetic energy is the energy in motion. So you see kinetic energy every time you move, every time you throw something, every time there's like you see an object moving, it's kinetic energy. Okay, kinetic energy is also shown in like heat. Okay, so when like the particles are moving, right, like that has more heat, and that's kinetic energy. Next is, so that means like when it's hotter outside, that means like there's more kinetic energy around you because the particles are going to be moving faster. Then we have potential energy. Potential energy is energy stored in an object due to its position. Okay, potential energy comes in many different forms, right? Potential energy, the ones that we see in physics class or in AP1 is gravitational force and electric potential energy, right? But there's other types of energy, or potential energy, like chemical energy, is a form of potential energy, right? So potential energy is the energy that is stored, right, in an object because of its position. So in terms of gravitational potential energy, when we lift something up because we're giving it height, right, we're it's going to have this potential energy, right? It's going to have this energy stored, right? Because remember, we're going to apply energy to lift an object up, right? Every time we lift up an object, we know that we're going to apply work, right, to lift up that object, meaning we're giving energy to that object. Okay, and that energy is going to be gravitational potential energy. Similarly, with elastic potential energy, when we're talking about springs or let's say rubber bands, right? When you're, let's say you're playing with like a bow and arrow, and like you stretch out the, or you I don't actually know the term, but let's say you stretch out the string in the bow, right? You're applying a force, you're putting a distance in that with that force, right? And you're giving it energy because you have to apply the energy to be able to pull the string in that bow, right? So before you're releasing it, you're giving it a potential energy. Okay? And that's going to be the elastic potential energy. So we talked a lot about work. Work is the transfer energy, right? So the work is how you're transferring an energy. Because remember, the law of conservation of energy. Energy is constant, right? The amount of energy in the world, the amount of energy in the universe is the same now as it was 4 million years ago. Because energy is neither created nor destroyed. Meaning, in a closed system, the total energy will not change unless there was work done on the system. Okay, so work is the transfer of energy, right? So what you notice here, so again, let's say you have like, let's say your phone fell to the ground, right? So your phone's on the ground and you're gonna pick it up. Okay, so you're gonna pick it up. So you're going to transfer energy from yourself, right, into potential energy for your phone because you're lifting up, you're giving it height. So that's what work is. It's a transfer of energy. So when you're like, let's say, you roll a ball, right? So let's say you roll a ball, but then it stops, right? So like, wait, how does it stop if the amount of energy should stay the same? Well, because friction is doing work, right? So friction is being applied in the opposite direction over a certain distance, doing work and taking away some of that energy. Okay? So work is the transfer of energy, and it's found using this equation. For work is equal to force times distance. So to be able to do work, right, for work to happen, right, you need to apply a force, right, over a certain amount of distance. So you like pushing a wall is you not doing work. Okay? You're not doing work if you're not applying a force over a certain amount of distance. So that's super duper important. So work is force times distance. Next is the law of conservation of. Okay, we just talked about that. Okay, so here are equations that we're going to need to know besides, work is equal to force times distance. Is first is the kinetic energy, 1/2 mv squared. So the kinetic energy of an object, right, like how much energy the object has is dictated on its mass and velocity. Okay, so this is super important, but since velocity is squared, a change in velocity will have more impact than the change in mass. So let's say your mass and velocity goes up by both like twice, right? So mass goes up by 2, velocity goes up by 2. Velocity is going to have much more of an effect, right, in increasing the kinetic energy because of the squared, right? It's just how math works. Next is gravitational potential energy, is mass times gravity times height, right? If we give something height, we're giving it potential energy. Next is elastic potential energy. It's 1/2 kx squared. Again, it's dictated on spring constant and the distance that you're displacing the object away from equilibrium, right? Meaning like in its happy position. So if you're taking it away from equilibrium, if you're stretching it or compressing it, you're giving it potential energy. Or it has potential energy. Okay, so now let's look at the graph, right? So the graph that you might see is a force times distance graph, or a force versus distance graph. Yeah. So a force versus distance graph, it's pretty, right? It might look something like this: a force versus distance graph, right? When you see a graph like this, just know that the area is equal work. Okay, so the area that you find in the force times distance graph is equal the amount of work done. Should be pretty simple. Okay, so next let's do power. Okay, so power is directly relevant to work. So power, sorry, I don't know what's going on here. So power is the rate at which you do work, right? So like how fast are you doing the work? How much energy are you transferring, right, per second? Okay, how fast are you at transferring energy? Okay, so pretty much like an object has more power if it has the ability to transfer energy, right, at a faster rate. Okay, so what that means is, like, for example, with your charger, right, your charger transferring energy into your phone, right, the faster chargers are doing more work, or has the ability, or has more power, right? They have more power because they're able to transfer more energy over a shorter period of time. So power is dictated or found using this equation. Power is equal to work over time, right? So the amount of work you do over a given amount of time. So let's say you do like 300 joules of work, right, over 3 seconds. That means you have 10 watts, 100, my bad, 100 watts of power. Okay, that's pretty much what it means. And it's denoted, or it has a unit of watts, or W. Yeah. So next, let's do momentum. We've talked about momentum a lot over the past few days. So momentum is mass in motion, right? It's mass with velocity. If an object has a mass and it's moving, it has momentum. So right now we're going to talk about linear momentum. So the units for momentum is kg meters per second, or kg times meters per second, and it's found using the equation P is equal to mv. M is mass, V is velocity, P is momentum. Okay, so momentum is, and it's super important to understand, is that the direction of the velocity is the direction of the momentum, right? Meaning, like, if the object is moving this way, then the momentum, so if V is moving this way, then P is also going in that same direction. Okay, so momentum is a vector quantity. It's very important to understand that that momentum is a vector quantity. So if we have an object with a momentum of, let's say, like 2, and then another object with a momentum of also 2, but they're in opposite direction, the momentum of the entire system will just be 0, because 2 minus 2 is 0, right? That's how, like, vectors would work. Very important to understand that we have something called the conservation of momentum. So meaning, what that means is the momentum of the system before is the same as the momentum of the system after, right? So the P before and the P after will always be the same. So an example I have here, right, is that I have like two 2-kilogram object moving in, or one of them is moving in 1 meters per second to the right, and the other one is not moving. Okay, so the momentum before, right, the only thing that's applying momentum, or that is having momentum, is the 2-kilogram object. No, there's no specific formula for elastic collision. It's just like there's no specific formula. You just, like, have to understand how an elastic collision differs from the other types of collision. Okay, and I'll show you that in just a little bit. Okay, so here I have an object. The only thing that's applying momentum is the 2-kilogram object, and you do 1 times 2. So the momentum of this is 2, the momentum of this is 0. So the momentum of the entire system together is 2. So the PB, right, is equal to 2. So that means that since we have the conservation of momentum, the P after must also be 2. Okay, so here what we know about after is that the 2-kilogram object is moving to the right at 0.5. Right? So I can find the momentum of this. 0.5 times 2 is 1. So that means since the momentum of the two objects has to add up to 2, the momentum of this object on the left also has to be 1, right? Because 1 plus 1 is 2. So if the mass is 2, right, what velocity times 2 gives me 1, and that will be 0.5, right? That should be, again, not too difficult. So here we're talking about the different types of collisions. We have elastic collision, inelastic collision, and perfectly inelastic collision, right? So elastic collision is when the objects bounce off each other and kinetic energy is conserved. So this is super important, right? So what you do here, and this is what Eric asked, is like, hey, how do I know it's an elastic collision? How do I know that it's an elastic collision? So one, you have to see, like, do they bounce off each other? Like, yeah. Cool, they bounce off each other, right? But also what you can do is you can find the kinetic energy of the system. Okay, so it's very, very important to understand that the kinetic energy is a scalar quantity, right? So we have scalar versus vectors. Vector quantity shows shows direction. Scalar quantities don't, right? So scalar quantities don't have a negative, right? It's just a bunch of positives. So energy is a scalar quantity. Work is not. Work is a vector quantity, but energy is a scalar quantity, meaning like you can only have a positive amount of energy, right? There's no such thing as a negative amount of energy. So, again, so what you can do is you can find the kinetic energy of the system before and the kinetic energy of the system after. So if I like zoom in here, like I can find kinetic energy using this equation, right? Ke is equal to 1 half mv squared, right? So I can easily figure this out. I know that this has a mass of 2 and a speed of 3. So I can find the kinetic energy of the system before. I can do like 1 half, m is 3, v is, m is 2, and then 3 squared, and then plus the kinetic energy of this ball, right? And again, even if they're moving in this opposite direction, kinetic energy is scalar, so that doesn't matter. It doesn't matter if they're moving in opposite direction. So we have 1 half 2, right, 4 squared. Okay, so we're going to add this up, and the kinetic energy of the system after 3 squared is 9. 1 times 9 is 9. 4 squared is 16. 16 times 1 is 16. So if you add this up, energy. Okay, so the kinetic energy of the system before is 25 joules. Now let's find the kinetic energy of the system afterwards, right? So we're going to have 1 half to 4 squared plus 1 half to 3 squared, and then you're going to find out that's also 25 joules, right? If you notice that, hey, they have the same amount of kinetic energy, then it must be an elastic collision, right? Because the kinetic energy is conserved. And very important to understand here, right, is that the kinetic energy, the momentum of all 3 different kinds of collision is conserved, right? So in collision, inelastic collision, and a perfectly inelastic collision, the momentum is always going to be conserved. But only in an elastic collision is the kinetic energy conserved. Okay? So again, you're going to be like, hey, if they bounce off, I know it's going to be one of 2 things, right? So it's going to be an elastic collision or an inelastic collision. Because in an inelastic collision, right, once they hit each other, they're also not going to stick together, right? But there's going to be energy loss, right? So the difference between an inelastic and an elastic collision is that a kinetic energy is conserved in the elastic collision, right? And you can figure that out by just like calculating it. So a perfectly inelastic collision is completely different. A perfectly inelastic collision is when the objects hit each other and then they get stuck together. Okay, an example of it is like a car crash, right? When let's say a car hits another car and then they stick together, that's an example of a perfectly inelastic collision. Okay, in a perfectly inelastic collision, a lot of kinetic energy is going to be lost. Okay, I repeat, in a perfectly inelastic collision, a bunch of kinetic energy is going to be lost. Okay, so again, you can see like, hey, in a perfectly inelastic collision, if they stick together, then you know it's a perfectly inelastic collision, right? If they don't stick together, then you know it's one of these two. It's one of these two. Okay, and then you just find the kinetic energy. If you find the kinetic energy is the same before as after, then you know it's elastic. If you don't, then it's inelastic. Next is impulse, which is the change in momentum, right? So when an object, like for example a ball, right? When you throw an object at a wall, you know it's going to bounce in the opposite direction, right? You know how balls work. That's what it does. So you know before it hits the wall, right, its momentum is going to be towards the wall, right? But after it hits the wall, as soon as it bounces on the other direction, then you know that it's going to have a momentum in the opposite direction. That means, right, since momentum is a vector, if it's going to have a change in direction, that means there's a change in momentum. A change in momentum is impulse, right? Impulse is defined as a change in momentum, and it's delta P. Okay, so you can find delta P, or change in momentum, by momentum after minus momentum before. Okay, so that's pretty easy. You find the momentum of the system after the collision, and then you find the momentum of the object before the collision, and then subtract them. Super easy. Okay. Another example is like, let's say when you're catching a ball, right? So when somebody throws a ball at you and you catch it, right, you're gonna have a momentum towards your direction, but as soon as you catch it, it has a momentum of zero, right? Because it stops moving. If there's no velocity, that means there's zero momentum. So there is going to be a change in momentum because it goes from having momentum to having zero momentum. Okay. So impulse happens by you applying force. So if you remember Newton's laws of motion, right? For you to be able to change like the velocity of something, for you to apply an acceleration, then you need to know that you have to apply a force, right? So if you're going to catch an object, for you to be able to give it a velocity of zero, then that means your hand is applying a force on that ball, right? Because it acts as the unbalanced force. So what that means is that like force is directly related to momentum, to the change in momentum, and it's signified by this force. Change in P is equal to force times delta T. Okay, so where delta T comes in handy, or where it's applied, is, again, we talked about this before, but and I wrote it down here. But let's say like you're falling off, like let's say you're falling off a roof, right? Like let's say you jump off a roof and you're landing on a hard surface. Well, like chances are, if the height is like large enough, is that you're going to hurt yourself, right? You're going to hurt yourself is because what's happening there is the hard surface, the hard floor is changing your momentum from a high level momentum to zero immediately, right? But if, let's say, instead of landing on a hard surface, you're landing on a soft surface like a mattress or a trampoline, right? What happens there is it changes your momentum, but it changes your momentum from, like, let's say 100 to zero, right, at a slower rate, right? Because it's giving you time to stop. Because you're not stopping immediately, right? Because the surface, the soft surface, the mattress or the trampoline, is slowing down, right? It's cushioning your landing. Okay. Similarly, it's how like the airbags are useful, right? Let's say you get in a car crash and then you get lunged forward, and let's say there's no airbags and you hit yourself on the steering wheel, right? The steering wheel is kind of hard. It doesn't give you like time to stop, right? And so that means that the steering wheel is applying high amounts of force towards your face in order for it to stop, right? But when you're given like an airbag, what that does is it lengthens, or it enhances the amount of time it will take for you to stop. Since the amount of time goes up, the force will go down, right? The force applied to your face will go down, so that means it will hurt a lot less. Okay. Another thing about momentum is explosion, right? So explosion is when two objects that are stuck together, right, are, I guess, propelled apart. Right? Like grenades, right? Grenade shrapnels, right? When a grenade explodes, it's an example of explosion. It's the metals that make up the grenade are stuck together, but as soon as it explodes, they're propelled in many different directions. Okay. Another example is like, let's say, a bullet and a gun, right? We've talked about this before, but when you shoot out a bullet is in one system with the gun, but as soon as you shoot the gun, right, they're propelled away from each other. Very, very important to understand that explosions are also related to the concept of the law of conservation of momentum, right? So again, if you have a gun, right, before you shoot the bullet, right, you're going to have a momentum of zero because the gun and the bullet aren't moving before you press the trigger, right? But as soon as you press the trigger, the bullet is going to go to the right or going to go in one direction, right? But again, with the law of conservation of momentum, the momentum of the system before and after must be the same. So if the momentum of the system, of the gun bullet system, is zero, then the momentum after should also be zero. So what that does is, like, the gun, right, is going to be propelled in the opposite direction to cancel out that momentum. Okay, so to cancel out the momentum to zero, because momentum has to be conserved. Okay, and I drew out an example here. So next, let's go with circular motion. So, just in case there's any confusions, I drew out, like, I have radians to degrees and degrees to radians. How do you convert from one to another? Okay, make sure that you guys, like, look at that and understand that. Next is centripetal force. Centripetal force is not an actual force, but it's the sum of the forces that enables an object to move into a circular path, right? So when you're, let's say you have like a yo-yo and you're spinning it in, I know it looks cool. When you're spinning it in a circle, right, you know that like the tension from the rope is the reason why it's being spun in a circle. So that means that your centripetal force, your sum of the forces, your net centripetal force is just tension, right? But then I have an example right here with, like, let's say this is a roller. Let's pretend this is a roller coaster, right? So in this roller coaster, when, let's say, this object is moving in a circle, right, and the object is at the bottom of its travel, you know that like gravity and the normal force, right, isn't the same axis as like the force pointed towards the center of the circle. So that means these two forces together make up your centripetal force. That's why I have Fn minus mg over here, because they're in opposite direction, but they're the forces that make up your centripetal force. Okay, same thing over here. Let's say it's on the top instead of the bottom. We know gravity is pointing downwards. But we also know like normal force is now pointing downwards because it's parallel to the or perpendicular to the surface. So instead of like sum of the forces is equal to Fn minus mg, now you're going to add them together. Okay. Another important thing about centripetal force, instead of making it equal to ma, you make it equal to mv squared over r. Okay? So here I have an example of like the moon. Right? The reason why it orbits the Earth is because of centripetal forces, right? The centripetal force that is causing the moon to move around the Earth or to orbit around the Earth is the force of gravity, right? So the force of gravity is our sum of the forces, right? So right here, I wrote that. The sum of the forces that is causing the moon to go around the Earth is force of gravity, right? And I know some of the forces, c squared over r according to this equation, and then so you know this equation and this equation are equal to each other. Okay, and then you can solve like different things there if you want to solve for v, if you want to solve for r, right? Just up to you. This is torque. Torque is a force of rotation, the rotational force, right? It's like how are you going to rotate something? And it's in units, newtons times meters, or kilograms times meters squared over seconds squared. Okay, and it's found using this equation. Torque is equal to force times L, where L is going to be the distance away from the point of rotation. Okay, also important to understand, right? Like let's say I have a seesaw over here. Okay, right, and let's say this is the point of rotation. Okay, and let's say instead of applying a perpendicular force, I apply a force at an angle. Okay, so that force here is not counted, right? I don't like this force, right? I don't like this force. I only like perpendicular forces when I'm talking about torque. So what I have to do is I have to find the vertical component of whatever this force is, which is going to be F sine of 30 degrees. Okay, that's why it's FL sine theta, right? Because we will have to convert all of the forces applied into vertical forces, right? And again, distance is the L, it's going to be the L, the distance away from the point of rotation. So next is the moment of inertia equation, right? So torque is equal to the moment of inertia times angular acceleration. Okay, so this is kind of similar to force is equal to ma, except in rotational I guess in the rotational context. Okay, so force is the same as torque in this case, and then mass is the equivalent of the moment of inertia. And again, the moment of inertia of an object is dictated upon the shape of the object and its mass, right? So again, like if you look back into the figure skater problem, the figure skater, when he pushes them, the figure skater changes their moment of inertia when they change their shape, right? When they put their bodies closer together, right? And the moment of inertia of like a hollow object and like a full object is going to be different, right? So the moment of inertia is dependent on the shape and the mass of the object. And torque is equal to moment of inertia times angular acceleration, right? Angular acceleration is how fast is the rate of rotation changing, right? How fast is the rate of the change in angular velocity changing. Then we have the angular momentum as L. Angular momentum is equal to the moment of inertia times angular velocity, right? We've talked about that before. Next, we have gravity. The force of gravity is the force of attraction between any two objects. Any two objects, again, has a force of attraction, and it's found using this equation. Fg is equal to g m1 m2 over r squared. And this is going to be, g is a constant, right? And it's going to be this constant. Again, it's pretty simple to figure out. The next few equations for like angular velocities and stuff like that, right? So these right here is how are you converting linear things to like angular things, right? So over here, how are you converting angular velocity to linear velocity? And you just follow these equations, right? It's pretty simple. Over here, yeah, so over here you're given like the kinematics equation, and then over here you're given like the angular versions or the rotational versions of the kinematics equations. Okay, so just things like that. Next, and finally, we're going to talk about oscillation and simple harmonic motion. And simple harmonic motion, again, is the repeating periodic motion, right? The moon going around the earth is an example of a repeating motion, right? It's going to keep going around and round and round. It's a repeating motion, so it counts as a simple harmonic motion. A pendulum going back and forth, like in a grandfather clock, is an example of a simple harmonic motion. A spring being compressed and then like going back and forth after you release it is an example of a simple harmonic motion. Again, the ones that are going to be very important is going to be the spring and the pendulum. Okay. Before we talk about that, let's talk about like period and frequency. Right? So period is how long does it take for one cycle to happen. Frequency is how often does that cycle happens, right? So the relations between period and frequency is that they're inverses of each other, right? T is equal to 1 over F, F is equal to 1 over T. You can find the angular acceleration of an object utilizing this equation. Angular velocity is equal to 2 pi F. And then you can have this equation, x is equal to a cosine angular velocity t, to find the position, right? X stands for the position of an object during its harmonic motion, right? Meaning like how far is it away from equilibrium during its entire travel, okay? And a stands for the amplitude or the max displacement from equilibrium. So these are kind of important, but like nowhere near as important as the springs and pendulums, right? So the important things about springs and pendulums, is going to be these two equations. Okay, so it's going to be the period of a mass of a spring and the period of a simple pendulum, right? So the period again is how long does it take, right? How long does one cycle take? And it's found using this equation for spring and then this equation for pendulums. For spring, it's 2 pi square root of m over k, meaning that the mass, right, and the spring constant are the only things that matter when talking about how long does it take for a cycle to happen. For simple pendulums, right, the only thing that matter is the length of the rope, right, and gravity. Those are the only things that matter. So meaning, this is super important, right? So like, let's say I have, where do I draw this? Okay, so let's say I have two pendulums. Oops. Okay, so let's say I have two pendulums, right? One, I start like right here at a big angle, right? Oops, sorry. I start right here at a big angle. Okay, and then one that I start right here at a small angle. Okay, so let's say one pendulum motion is at a bigger angle and one pendulum motion is a smaller angle. Let's say the mass is equal, right? The mass of, let's say this is A and this is B. Mass of pendulum A and mass of object B are exactly the same. Okay, so mass is the same, right? And let's say they're both on Earth. That means that the gravity is the same. Okay, since that means, right, with the equation for the period, 2 pi square root of L over G. Okay, so when we have this equation, since, right, even if, okay, even if the angle is a lot larger, okay, even if the angle is a lot larger, right, since L is the same, sorry, not M, L. Okay, let's say the L here and the L here are the same, so LA, LB are the same, okay? Since the length of the ropes are the same, right, and gravity is the same, that means that the period of oscillation for A and the period of oscillation for B are going to be exactly the same, right? So that means like the time it takes for this to go there and then come back, and the time it takes for B to start here to go here and then come back is going to be exactly the same, right? Even with like the massive difference in the angle, right? That doesn't matter. The only thing that matters is the length of the rope and gravity. Similarly for let me draw it here. Similarly for a spring, right? So like let's say one I like compressed this much and the other I compressed even more. Okay? So this one has a more of like let's say this is equilibrium. Okay, let's say I made this too big. Okay. So let's say yeah, this is equilibrium, right? So if you notice the distance here is bigger, right? So the XB and XA. So you know that like XA is going to be smaller than the distance B, right? But that doesn't matter, right? Because according to this, right, the period for a spring is 2 pi m over k. The only thing that matter is the mass of the two objects and the spring constant. If those are the same, then the period of oscillation is going to also be the same. So I repeat, the only thing that matter for let's say for a spring is the mass and the spring constant, and the only thing that matters for a pendulum is the length of the rope and gravity. Okay. So again, the idea of like simple harmonic motion is the idea of like there's going to be an equilibrium, meaning like where an object is at its happiest, right? The spring is happiest when it's not stretched or pulled, right? Or pushed, I guess, or compressed. A pendulum is the happiest when it's right in the middle, right? When it's not in those positions, there's going to be a force that's trying to get it back to that position, right? So with a spring, when you pull a spring, the force on the spring acts as a restoring force, and that's F is equal to negative kx, right? For a pendulum, when the pendulum is not in the middle, gravity is trying to put it back in the middle, right? So that those are the restoring forces. Another important thing is the concept of like graphs in here, okay? Or sorry, the concept of like way energy works in simple harmonic motion. So even with a spring or a pendulum, we know when it's at amplitude, meaning where it's like far away from equilibrium, furthest away from equilibrium, we know it has potential energy. As soon as you release it, that potential energy is slowly going to turn into kinetic energy. When it reaches equilibrium, all of that energy becomes kinetic energy, right? And then it's like stretched again, becoming potential, then going back to kinetic, then potential, kinetic, potential, over and over and over again. Okay? So this is like it's just like a graphic that I drew. Another important thing, the last thing that we're going to cover are graphs, right? I drew out like graphs that are possible, that you can see possible when it comes to like the motion. And all of these graphs is very, very important. All of these graphs are starting at amplitude, right? It's starting at either when it's fully stretched or fully compressed, or in terms of a pendulum, it's starting at like when the pendulum is at its amplitude, meaning like away from equilibrium. Okay, so here is a position versus time graph. We know, super important, when it's an amplitude, we know like the position will be away, it will be not zero, right? This is 0, its amplitude will be at its position will be away from 0 at its like maximum point. That's why like right here, when let's say we're starting it stretched out, it's going to have a position away and the negative position away from 0, right? And then when it hits equilibrium, okay, it has a position of 0, assuming equilibrium is 0, right? And then when it hits the other side, it will have a maximum displacement on the opposite direction, okay? So that's for position versus time graph. For velocity versus time graph, remember, when it's fully compressed, right, it's going to only have potential energy, meaning it has no kinetic energy, meaning it has no velocity. That's why the velocity here is 0, at its starting point. When it reaches equilibrium, right? It's going to have a maximum velocity because that velocity becomes all, or that energy becomes all kinetic energy. So it's going to have a maximum amount of velocity. Then when it reaches the other side of the amplitude, it's going to have a velocity of 0, right? And then when it reaches equilibrium again, it's going to have a negative maximum velocity, okay? Because it's going in the other direction. Acceleration, very similar. Acceleration. So again, remember, acceleration and force are like the same thing, right? Because force causes acceleration. So if you think about it, when an object is fully compressed, you feel like the force really fighting back. So that means that's when the force is at its highest, at its starting point, right? If the force is at its highest, then acceleration is also at its highest. When it reaches equilibrium, it's no longer being compressed or stretched, meaning it has a force and an acceleration of 0. Okay, so that's equilibrium. And then on the other side, it's going to have that same thing, but in the opposite direction, and then it's going to keep on doing that cycle. So what you guys should take note from these graphs is that, like, I only drew like parts of the graph, but the pattern will be like continuous, like forever and ever and ever. Okay. The other thing is a total energy graph, right? A total energy versus time graph. Know that the total energy does not change, right? Like, remember, energy is conserved, so the total energy is going to be the same throughout. The only thing that changes is what kind of energy it is, right? So here I have potential and kinetic. The potential energy graph, when it's fully compressed, it has the most amount of potential energy. When it's at equilibrium, it has 0 potential energy, and then it just goes back and forth, back and forth. Same thing with kinetic energy. When it's fully compressed at its starting point, it's going to have a kinetic energy of 0 because it's all potential energy. When it reaches equilibrium, it has a maximum amount of kinetic energy. That's why it's like an amplitude, and then it just does that cycle over and over and over again. Okay, so these are our graphs, and these are basically what's going to be covered on the exam. Again, if you have any questions, right, over the next few days, please don't hesitate to email me. I'll try to like get that answered. Again, if you haven't done so already, please fill out like the Google Forms I posted on Google Classroom. It's very important they get that information. Yeah, so like make sure that you guys know how to access the exam. If some of you guys, when are you guys taking the U.S. history test? Like the sophomores? Friday? Oh, it's Friday. Damn. Okay, that's scary. Okay. So it's just one. It's just the document based. Yeah, it's a DBQ. You guys don't even need to know history. You just need to read. Should we, right? Like that should be like the easiest question, because you don't have to remember anything. You just have to like base your answer on the document. Yeah. Okay, so again, like if you guys have